Great, the live stream started. We are ready to start this great session on bug localization and test isolation. And today we are going to have three great talks. The first talk will be given by Michael Pradell from University of Stuttgart. And the first talk is a scaffold bug localization on millions of files. Michael, the stage is yours.
All right, thanks for the introduction. Can you see my slides and hear me?
Yes.
Cool, all right. Yeah, then thanks for joining this talk on Scaffold, which is an approach to localize bugs that cause a crash in your software in a repository that contains millions of code files. This is joint work with Vijay, Rebecca, Mateusz, Eric, and Satish, who are all with Facebook. And I'm at the University of Stuttgart, but I did this work mostly while I was at a sabbatical at Facebook. So let's start with the motivation. Yeah, despite all our efforts of creating correct software still sometimes crashes, and sometimes these crashes happen in the field. And if you have software that is used by billions of people, then you actually may have thousands of such field crashes every day. So the challenge is how to localize the place where you should fix these bugs in a very large code base, for example, a code base with multiple millions of files. Doing this is relevant for a couple of reasons. One is that it will help you to find the right team or right developer within a larger organization who's responsible for fixing a bug. Second, it's relevant for giving this developer a starting point. So if you can tell the developer where this bug is likely to be fixed, that's of very big help. And finally, localizing bugs can be very useful to enable automated program repair, because typically these techniques assume that you know where to fix the bug. So now in this work, our goal is crash-based file-level bug localization. So let's have a look at what exactly I mean by this. So when I say crash-based, I mean that the only input that is given to our approach is what I call a raw crash trace. And raw crash trace here basically means it's a text file, and we do not assume anything about the format of this text file. That gives us some evidence about a crash that has happened. And we'll see an example or two examples of such a raw crash trace in a few seconds. File-level bug localization means that what we want to know is the file, or maybe the set of files, in which you are most likely to fix the bug that has caused the crash. Of course, ideally, we would like to get even more fine-grained information, for example, the exact statement that you want to fix. But in practice, this is very difficult. So here we focus on localizing the right file, so file-level bug localization. To make things more concrete, let's have a look at two examples of these raw crash traces, and here is one of them. So this is a crash trace created by a Java application, an Android application actually. And what you can see is that these crash traces contain tens or sometimes hundreds of lines. It's all raw text, so we do not really know much about the format of these lines. And what you can also see is that there are different kinds of information. So for example, here you see a stack trace. There may be even more than one stack trace, for example, if one exception has caused another one. Or down here, you see some additional information about this crash, like what app exactly has crashed, some information about the device on which this app was running, and many other things that are all in this raw crash trace. Now, this was an example from an Android application, just to show you that we have different kinds of these crash traces. Here's one from a server-side application that is written in PHP. And as you can see, it looks very different. So there's some similarities. So again, there's something like a crash trace, but then the format and also many other details just differ. And we actually have many of these crash traces, and they come in different formats and shapes. Now, given such a crash trace, there are a couple of interesting challenges that we need to address in order to localize where to fix the bug that has caused this crash. The first of them is about scalability. So the code base we're interested here is a code base with multiple millions of files. So many existing approaches that, for example, assume that you can statically analyze all this code just don't really work well, because you cannot easily apply them at this scale. This code base is not only large, it's also very heterogeneous, by which I mean that we have code written in different programming languages, code running on very different platforms, server-side, mobile, web, and so on, and code working in very different domains. And finally, the third challenge is that we need to deal with sort of fuzzy information, because the information that we have about the crash given in this raw crash trace may not exactly match, for example, the information that we see in the code base. For example, because the crash is based on an older app than the current code base. Now, of course, we are not the first to look into bug localization. In particular, there are two very interesting streams of prior work that I would like to briefly mention here. One is based on traces of correct and buggy execution. So given such traces, you can try to localize where to fix a bug. These approaches are really great, but they require a test that reproduces the bug. But now for the field crashes we're interested here, we typically do not have such tests. Otherwise, the problem would already be half solved. But so we can't really apply these approaches. Another line of work looks at some evidence of a bug, for example, a stack trace or maybe a human-written bug report that tells us about this bug. So in some sense, these approaches are very similar to our approach because we also have an evidence of a crash as an input. But what we found by looking at these approaches is that they all suffer from some kind of scalability problem that prevent us from applying it to the large code base we're interested in here. For example, because they assume that you can statically analyze all the code. And finally, practically all existing approaches focus on a single programming language, but here we're interested in a very heterogeneous code base. So we would like to have an approach that works for more than one language and does that in an easy and natural way. So our approach to address this challenge is called Scaffold, and here's a rough overview of how it works. So as an input, we're given a crash trace, and you've now seen what this is. And what we would like to predict as the output is the file, or maybe the set of files that you need to change in order to fix the crash that has been evidenced by this crash trace. The key idea of our approach is to decompose this problem of predicting the right file into two easier subproblems. And these easier subproblems are addressed by these two main components that you see here. So the first of them is what we call a trace line model. It will essentially tell us which of the many lines in a crash trace are most relevant to localize the bug. And then given these relevant lines, or maybe just one very relevant line, we're using an information retrieval-based search that will then help us to predict which file to look at in order to fix the bug. And these two problems turn out to be easier than the end-to-end problem, which is why we are decomposing the problem like this. So let's have a look at these green boxes and look at some more details. And let's start with the trace line model. So the trace line model is a machine learning model that, given a crash trace that consists of lines of raw text, predicts what we call a relevance vector. So basically a vector of numbers that tells us how relevant each of these lines in the crash trace is for localizing the bug. Now, why do we use a machine learning model here? One reason is that we have these many different formats of crash traces, and we would like to learn from existing data how to read these crash traces instead of hard coding how to do it for the many different formats that exist. Now, in order to do this machine learning approach, we need some training data to train a model, and we get this training data from past crashes. So in the past, of course, software has also crashed, and we have some crash traces for which we know which files have been changed in order to address this crash. And we use this to generate some training data for our traceline model. So what this training data basically tries to find out is which lines in this given crash trace are most relevant to locate the fixed files. To get a ground truth for this relevance, we look at all the tokens that occur in these lines of the crash trace. And we also look at all the segments of the file paths of the files that were changed to fix the crash. And then we compute the overlap between these two sets of tokens and segments. And the more overlap we see, the more relevant we assume a line to be. So getting back to one of the two examples I've shown, let's assume that this bug that has caused this crash needs to be fixed in the file do stuff browser controller.java. Then what we would get from this is that these three lines are the most relevant to find out this file, because actually they mention this file. Now, giving ground truth created that way, we can then train a machine learning model, and specifically we're using a neural model here. It works as follows. So the input is a raw crash trace. which we first represent as vectors by tokenizing every word or every token that occurs in a line. We do this using using a pre-trained virtual word embedding that essentially gives us a sequence of vectors for all the words in a line. Then we analyze each line in separation using a recurrent neural network that summarizes an entire line into a single vector called a line vector. And then based on the sequence of these line vectors, we have another recurrent neural network called the trace line RNN, which then summarizes the entire sequence of lines into a single vector called the trace vector. And this trace vector is then finally given to a fully connected layer, which eventually predicts this relevance vector. Now, zooming out again a bit, now you know basically how this first part of the approach works, which tells us, given a raw crash trace, which lines are the most relevant. And now the second part of the approach is an information retrieval-based search that looks at only the most relevant lines instead of all these hundreds of lines, and then predicts which file is most likely to be responsible for the crash. So let's have a look at this second component and this information retrieval-based search. So essentially what we take as the input here is a line in a given crash trace. And what we would like to predict is the paths in the code base that are most relevant for this particular line. Typically, if you use information retrieval, you have some kind of query and you want to match this query against a set of documents. And in our case, this query is basically a line in the crash trace. And the documents are the paths of the files that exist in the code base. Now, to do this matching, we tokenize the line in the crash trace into words. So for example, for one of the lines that you've seen earlier, we would get this set of words that occur in a given line. And for all the paths that exist in the code base, we tokenize them into their path segments. So let's say we have a path like this, then we would tokenize it into project X, package A, do stuff, and so on. And then we would give this query, which is a set of words, and this huge set of words that each represent a file into an existing IR-based search and retrieve the most relevant paths for a given line. So after talking that much about the approach, let me have a look at the evaluation. So this work was evaluated on around 20,000 crashes of various different Facebook products running on Android and iOS, and also server-side crashes in PHP code. The code base we consider here is the monorepo that Facebook uses to store most of its software. So it's a multi-million line of code, multi-million files repository. So it's a really huge repository, much larger than what you see in most open source projects. And the data we are considering here was gathered over a four-year period, which we separate into 50-day steps. So to make the evaluation more realistic, we basically take all the data that came in up to some point, and then use this data to train a model, which we then evaluate in the next 50 days. And then after 50 days, we basically do the same, take all the past data and evaluate it in the next 50 days. So this mimics a realistic setup for this kind of model. So let's have a look at the results. In this presentation, I will focus just on the end-to-end effectiveness results, which basically tell you how many times this whole approach is successful in predicting the right file or files for a given crash. So what you see here on the horizontal line is these different 50-day intervals. So basically every point is one point in time. And on the vertical axis, you see out of all crashes that appear in this 50-day interval, how many can we predict for how many can we correctly predict the right file to fix. What you see here is the result for Scaffold, so our approach. And as you can see, it's successful in roughly 60% of the cases. So it does not always work, but in many cases, it is actually able to localize the bug. We compared Scaffold to a couple of baselines. One of them is a heuristic logic that is currently in use at Facebook, which is basically a hand-coded version of the model that I'm presenting here, which has a couple of heuristics for different kinds of raw crash traces and tries to find the most relevant file based on a set of heuristics. As you can see, that heuristic logic also works pretty well, but Scaffold actually works better. And one reason is probably that it generalizes from all the data it can look at during learning instead of relying on a few hard-coded heuristics. We also compare Scaffold to an end-to-end information retrieval-based search, where we basically take all the words in a given crash trace and try to match those against the paths in the code base. But this does not work very well, showing that this decomposition into two subproblems is actually worthwhile. We also looked into a prediction based only on stack traces, because a lot of prior work has looked not at these raw crash traces as we do, but only at stack traces. So here we extract the stack traces and then just feed those into Scaffold. And what you can see is that it also works pretty well. So it's the same metric that you see on the vertical axis. So how often do we predict the correct location? And again, this is around 60%. As another baseline here, we consider an approach that we call first lines first. It's something that was suggested in prior work that basically assumes that the first line in a crash trace is the most relevant, but this turns out to not work that well. And again, we also compare to an end-to-end IR-based search, which again does not work that well. So beyond these numbers, it's interesting to ask why this works or why this does not work. And we identified three aspects here. So one is about the question whether the buggy file is actually mentioned somewhere in the trace. So all the approach gets as an input is this raw crash trace. And if the buggy file or not even part of it are mentioned anywhere in the crash trace, then the approach does not really work well because it just doesn't get the necessary information. Another dimension is how well Scaffold can handle partial information about files. So sometimes you may have parts of a file name, but the path is not the same because on the device, the paths are different than in the code base. And depending on how well Scaffold can handle that, it will be successful or not. And then the third dimension is about understanding the structure of these raw crash traces. So this traceline model actually learns to identify stack traces and learns to understand the different segments of a stack trace and which parts of them are probably more relevant than others. And depending on how well that works, the whole approach works better or not so well. As usual, there are many more details in the paper, so I don't really have time to go into many things, including more details on the data set, efficiency, and a more detailed comparison to other baselines. But yeah, if you're interested, please have a look at the paper. So to wrap up, I've presented Scaffold, which is a scalable approach for bug localization on millions of files. The key idea that you should probably take away from this is that you can decompose this bug localization problem into these two subproblems of identifying the most relevant line in a given crash trace, and then matching this relevant line against a path in a code base. The approach is learning-based and language independent, which has the advantage that it's pretty easy to adapt it to an evolving code base. So if another programming language becomes popular, or if the format of these crash traces changes, then all you have to do is to retrain the model instead of having to adapt the approach itself. And with that, I'm at the end of my talk, and I'll be happy to take any questions.
Thank you very much, Michael. This is a very nice talk. I welcome everyone to for a virtual round of applause. And we have one question on Slack. I will read that to you. And it's from Andreas Zeller. First of all, cool work. And did your evaluation take into account that bugs may be unevenly distributed? Say, if it's always the same 10 files that get fixed, it's easier to predict them.
Yeah, that's a pretty good point. So the bugs are definitely unevenly distributed, and they're definitely not just in the same 10 files. Given the multi-million file code base, the bugs occur in many different files, but it's true that there's some files that are more likely to be the root cause of a bug. Since the approach does not really look at all, so an alternative approach we considered, and that is discussed in more detail in the paper, is to formulate this problem as a classification problem, where we would look at the files and then classify which of these files is the one you should fix. If you would take that approach, then the model could basically learn which files are more likely to be buggy. But it turned out that this approach doesn't really scale to millions of files because classification is not really made to work with millions of different classes.
Thank you. And just one more quick question. And this is always from Slack, from Rohan Padie. Nice talk. Be honest, I'm surprised with your results because I was not expecting the buggy file to be mentioned in the crashes log that often. Is there anything particular about the frameworks used or other course style of software design in the corpus that makes this possible? For some reason, this does not match my intuition based on my own experience debugging my code. Alternatively, do you think this will generalize to other code outside of Facebook?
Yeah,
and here, like a quick answer, if you can have for this, and then maybe we can follow up that on Slack.
Sure. So I think one property of the code base we looked at here that is specific to Facebook is the size. So there are some other code bases of that size, but not all code bases are like this. Regarding the question whether the buggy file is mentioned in the crash trace, it's not always, right? That's why it only works in around 60% of the cases. But in those cases, the buggy file is indeed somewhere in the crash trace, and that's why it works. This observation is not completely new. So some other work on bug localization has also reported that often, but not always, you find the buggy file somewhere in a trace. The question is how to find it and how to match it with the code base, and that's what we address here.
Thank you very much. And again, nice talk. And there is one more question on Slack I posted from Zoom. So if you can take that on Slack, it would be great.
Sure, thanks.
Thank you very much. And now we can move to the second presentation. This presentation has received the ACM Distinguished Paper Award. It also has received 3 artifact badges. The work was evaluated to be available, functional, and reusable. And Rahul Gopinath is going to present this work. And the title of the work is Abstracting Failure-Inducing Inputs. Before I let you start, Rahul, I want to mention that on the screen, I can see your presenter notes, not the slides.
Thank you. Let me do that again. Is this better?
Yeah, this is the right one. So without any further ado, I let Rahul present the work.
Hello, I'm Rahul Gopinath, a researcher at ISSTA Helmholtz Center for Information Security, Germany. And I'm here to talk about our work on abstracting failure-inducing inputs. For first thing, we feed the program with generated inputs and check the program behavior. Sometimes the program fails. So what caused the failure? In this case, we can actually form a hypothesis based on the patterns seen so far. It's quite possible that the program fails when it sees a nested parenthesis in the input. However, quite often, the input is extremely large and difficult to debug. So when considering such large inputs, it's not immediately clear why the program failed. The traditional technique for input reduction is an algorithm called delta debugging. Essentially, we start with a failure-inducing input such as this and split it into fragments. And then we attempt to remove the fragment, one fragment at a time, while preserving the failure. If we cannot remove the larger parts, then we remove smaller parts and still smaller parts, until we reach the smallest input that can still reproduce the failure. And this is returned to the user as a minimized string. However, there's a problem when it comes to structured inputs. That is, inputs such as those to an interpreter. The syntax of such inputs is commonly described using context-free grammar And these are, the trouble is that the interpreter expects every input to the program to be syntactically valid. So the trouble with delta debugging is that it's not structure aware. So it fails in identifying fragments that can be removed without causing a syntax error. That is, we have to use techniques that can generate inputs without the syntax error. And there are modifications to the traditional delta debugging that can adapt it to work on structured inputs, collectively called hierarchical delta debugging. And these techniques first use a context-free grammar to parse the input into a parse tree. So here is an arithmetic expression and the grammar that describes the arithmetic expression language. And we use the grammar to parse the input into a parse tree. The idea is to find smaller but valid trees that still produce the same failure. So we recurse through the nodes, and at each point, we replace the nodes in the tree by smaller nodes that can reproduce the failure. And we repeat the procedure again and again until we get a minimal string. And that is returned to the user as a result of minimization. That is, we can reduce the larger expression into a much smaller expression that can still reproduce the same failure. However, this minimized string leaves a number of questions unanswered. Before prioritizing a fix, a developer may need to know a number of things about the behavior of the code, and also does the failure occur in the inputs. For example, the developer may want to know if the failure is caused due to minimal length. So can something, a completely different string that is 5 characters long, reproduce a failure? Or is the failure due to the number 4? What if we replace the 4 with something else completely different? Or is it because of the double parenthesis? Or can just 2 parenthesis expressions reproduce the same failure? Or does it have something to do with the fact that negative sign is not used? Any number can be used, or a variable. So the developers need to know all these answers, the answers to all these questions before forming an initial judgment on what part of the program was actually involved in the failure. And to see that in the real world, here are a number of minimized strings that were reported in real world programs. So here is an issue from closure that causes a failure. What caused the failure? Is the empty class important? What about this one? This is again another issue from closure. So are these variable names L0 important? Can we replace them with anything else? What about this particular issue from Rhino? Does all the variables have to be named exactly as Baz? Can we replace them with anything else? And here's another one. Is the Y important here, and why is it an empty array? So the trouble is that none of these minimized strings are actually informative. And in many cases, as you will see, the initial idea formed from a casual inspection is incorrect. So the question is, can we do better? Given a short string such as the ones that you saw before, can we further extract the causes of the failure and identify the most important parts that were actively involved in causing the failure? And our technique called DDSet can identify which parts of the input is actively causative and what part of the input is just a filler, and that too with high accuracy and precision. And here is how DDSet works. As before, DDSet starts with a context-free grammar for input and then generates a parse tree. Then we start with a root node and then use the context-free grammar to replace the node with an arbitrary generated node of the same kind. And we try to generate nodes such that the generated inputs are also semantically valid. And if any such semantically valid nodes are unable to reproduce the failure, then we mark the node as complete and continue. In this case, this generated node 1 times 2 minus 3 does not reproduce a failure. So we mark it as concrete and we look for the next node in the tree. So here it is expression, and we follow the same procedure of random generation of valid nodes. And as before, 1 plus 3 plus 4, which is generated, does not reproduce a failure. So that is marked as concrete. And the next one is term, and we follow the same procedure. And as before, the generated input 3 times 4 is not reproducing the failure. So term is also concrete. Continuing this way, we reach the last expression node, and that actually reproduces the failure. In fact, each expression produced by replacing the last EXPR node here with another randomly generated node induces the observed failure. That is, we can conclude that the expression node here does not contribute to the observed failure, and it serves just as a filler. So we mark that particular expression node that we just found as a filler as an abstract node. And once we mark a node as abstract, we stop recursing because none of the child nodes are necessary to induce a failure. And we can prune the tree. And extract the abstract failure inducing input. So here, double parenthesis EXPR, that's abstract pattern. And you can see that it precisely captures the predicate and it answers all the questions that we had about the input. However, that is not all. The abstract failure-inducing input produced using dataset can also serve as a generator for new inputs, all of which will now produce a failure. So let us see how dataset performs with real-world issues that we saw earlier. So here is what we were able to extract from the closure issue. The variable can be any, and of course the identifier can also be any. Here is the second issue from Rhino. And we found that the last variable declaration can be pretty much anything. But what about the name Bass? We do not know that yet. And here is an issue from Rhino. And unfortunately, we are not actually able to abstract anything from here. However, that is not true. The variable Y is plainly abstractable. It's just that the abstraction procedure that we use so far is not able to recognize it. So let us see why this happens. So consider this expression. As you can see, the variable V is repeated and then assigned to itself. And the error occurs only on self-assignment. So you have to use the same variable again. So the issue is that if we use the procedure that we followed until now, we only consider independent replacements. Replacing the first variable independently does not help. And certainly the second variable is not independent, and nor is the third one. However, it works if you can replace them together. And this is what dataset does. The idea is to recognize that the concrete nodes that remain after abstraction may vary together. So we collect the non-overlapping concrete nodes, group them under their respective node terminals, and then match them based on string matching. And then check whether these nodes can vary together. And we see that varying these fragments together can reproduce a failure. Again and again. If they can, then these nodes are indicated by a common variable name, here alpha 1. So here is the issue that we saw earlier from Rhino. And we can actually successfully abstract and identify the variables. Here is another issue from Rhino. And we find that the two locations contained causative interlinked variables, while the last one was not necessary. What was not necessary for the figure. It is the variable declaration is simply a filler there. And finally, this is the issue from closure. And we can actually successfully abstract this issue also. That tells you that the variables are actually important. They have to be the same. So we looked at a number of other bugs. And we found that on the whole, our technique produced 86% semantically valid inputs. That is, all the inputs that we produce are syntactically valid. But of those syntactically valid inputs, 86% were also semantically valid, and of which nearly 100% actually reproduce the failure. And that's pretty good. There is one more question there, though. Until now, we have assumed that the grammar was available. However, sometimes, quite often for that matter, the grammar is not actually available. The interesting thing is that we can actually mine the input grammar from the dynamic control flow. For that, see our FSC paper on mining input grammars on how that can be done. So finally, our technique is fairly simple and straightforward. Where do we go from here? One thing to note is that the mine patterns are not just failure-inducing, but also behavior-inducing. For example, we can mine patterns of input that say, we should cover this particular part of the code. And we have talked about how the abstract pattern becomes a producer. However, we can also refine the original grammar such that all the inputs produced by the grammar will be guaranteed to produce a fault. Or as a recognizer for such faults, to make sure that none of the faults that we recognize gets through. And that's not all. If you have many such independent refinements, we can also combine these refinements together to precisely control using a grammar what exactly you want to produce. You want to actually produce something that induces the same failure that you just fixed, or at least tries to. It covers the same code and does not go through the validation. And this is something that we are actually working on currently. And if you're curious about our technique and you want to learn more, we have both a blog post that actually details the entire thing, as well as a replication package that you can build on. So in summary, we have talked about the problems with traditional minimization, how DB set can abstract both filler parts of the minimized input, as well as identify the covariant parts, and how the abstract pattern that we derive at the end can be used by the developer. And thank you for listening, and I'll be happy to answer any questions that you have.
Thank you very much for the nice talk and great work. So I see that there are no questions on Slack at the moment. So I have a question. Were there any case in which you were not able to abstract the input inducing the failure? And if yes, what are the reasons why you were not able to abstract those inputs?
So I think there were one or two cases where we found this. The reason was that the failure that was caused was due to an extremely tiny string. And all the parts of the string were actually useful for inducing the failure.
Okay, thank you very much. I just see that another question came up. It's from Rohan Padier. And awesome work, first of all. And then, is there anything about context-free grammar that your technique depends on? It sounds like it is much more generally applicable.
So we need to be able to generate more and more inputs. So long as you have a generator like what Rohan is working on, this technique should be applicable. And if you're more curious about how this can be more widely applicable, you should see our FSC paper, Al Hassan, not mine actually, but from our same group, that goes for a much larger or much more generalizable technique.
Thank you for answering this question. So we have 1 more minute, and I have another question about the process of abstracting the grammar, the input. And can you provide a little bit more details on how the abstraction process works? For example, when you're trying to concretize one of the terminal in the grammar, you might generate a new failing input. So how do you recognize that that's not a new crash, or when you do stop the process?
So we do depend on a precise characterization of the failure. And if we cannot actually recognize a different failure, or if we come across a new failure, while generating this abstraction, then that essentially becomes, part of the pattern that we produce. So we can't really do anything about that. That said, there is more work that is coming from our group that will be tackling this soon.
Okay, thank you very much. Looking forward to this work. And again, congratulations for the Distinguished Paper Award. And we can move now to the third presentation of today. So I invite Pengyu Mi to share the screen. So we are in our last talk of today, bug localization and test isolation session. This work is done by Pengyu at the University of Texas, Austin. And the title of the paper is Debugging the Performance of Maven's Test Isolation Experience Report. The stage is yours.
Cool, thank you, Mathieu. Hi everyone, I'm Pengyu. So today I'm going to present a joint work with Ahmed, myself, Alex, John, and Miloš about debugging the performance of Maven's test isolation. So before I go into our contributions, let me first tell you what's our motivation. So we all know that testing plays an important role for ensuring the correctness of software. However, one severe problem that could compromise such assurance is what's called flagginess. So which means some tests might pass or fail non-deterministically without any code change. And the common practice to combat those flaggy tests is to run them in isolation from each other to eliminate some source of flagginess, such as test order dependencies. So what exactly does it mean to run them in isolation? So let's consider two extremes. So the extreme to the left here is what's called absolute isolation, which means for each test, I will use a fresh virtual machine and reinstall everything like operating system, build system, and the application on the test, and then run one of the tests. And when I move on to the next test, I will do the same again. So that offers guarantee that no test can affect each other, but comes with a very high cost. So on the other hand, there's no isolation, which means I just simply run all the tests in one process. And that's actually the default mode for most of the build systems nowadays. So the more isolation we implement, the better protection we get against flagginess, but at the same time, it comes with a higher cost. So what's actually most commonly used middle ground in practice is process level isolation, which means I will run each test in its own process. And in case of Java, that means forking a separate JVM process for each test case. So even though process level isolation is not the highest cost one, it still introduces substantial overhead coming from the startup cost of each process and inter-process communication. So to actually measure that overhead, we designed this exploratory study where we selected 3 build systems that implemented this process level isolation. And we asked it to execute a simple test, which is just to sleep 250 milliseconds. And we compute the overhead of the actual time for that test minus 250 milliseconds. So we did this for 3 build systems, Ant, Gradle, and Maven. So what's already interesting here is like these 3 build systems all have very different overhead because they have different implementation of how test isolation works. And what's surprising is like Maven has huge overhead compared to others. The overhead of Maven is more than double of that of Ant. So we want to understand that why in particular Maven has this huge overhead and if there exists a way to get rid of this overhead completely. And that leads to our contributions. So first we developed the FolksGrip, which is a novel technique to minimize inter-process communication overhead test isolation, which saves test execution time by on average 50%. And guided by the development of that, we found and fixed the performance bug in Maven's test isolation, and our patch has already been accepted and merged in Maven. And we did an extensive evaluation of FolksGrip and patched Maven on 29 projects totaling 2 million lines of code to evaluate their effectiveness. And finally, we will share some implications and lessons learned from our experience. So now I will get into details for each of these. And so this slide is to give you a bit more context on the test execution in Maven. So in Maven, there's a component called showfile plugin to manage test execution. And the default command mvn test simply executes tests with no adulation, which means all the tests will be executed in the same JVM process. So if the user wants to use test adulation, there are two command options for that. So dereuse Fox tells Maven whether to reuse the same JVM process for all the tests. And default count tells Maven whether like how many JVM processes can be running in parallel. So for example, when dereuse Fox is false and default count is 1, now Maven will run each of the tests in its own JVM process and one after another. But in this case, when default count is 2, now 2 test processes can be run in parallel. And what's actually behind the scenes, how showfile implements this test adulation, is illustrated in this figure. So there are 2 K classes, FolksStarter and FolkBooter. So FolksStarter will first create an executor which maintains a thread pool that where each thread is for running one of the tests. And for each test, FolksStarter serializes the configurations to a temporary file. And it starts the FolkBooter JVM. It starts a child JVM process whose main class is FolkBooter. And FolkBooter will deserialize its configurations from that file and then execute the test with JUnit. And finally, FolkStarter will wait for FolkBooter to send a goodbye signal when the test finishes. So without going into too much detail here, what I want to show is that there are many inter-process communications going on here, back and forth between these 2 processes. For example, the using of thread pool and executors, exchanging configurations via serialization, class loading of these showfile classes, and pumping input-output between the JVMs. And they are all very costly. So the question is, if can we get rid of this IPC process, like IPC? And the answer is yes. So that's what we developed in FolksGrip. So FolksGrip generates a single on-the-fly specialized execution script for running all configured tests and collecting test results. So in FolksGrip, there will be no inter-process communication between the build system and test processes, which means so what that means is FolksGrip actually relies on operating systems process management to start child JVM processes for running tests. So this figure illustrates the workflow of FolksGrip. Basically, when build system needs to run tests, it tells FolksGrip what are the tests to be run and what's the configurations for them. And FolksGrip will generate this script based on that, which invokes JVM processes to run the test. So, for example, so in FolksGrip, we support both using or not using test adulation and both sequential and parallel testing. And for example, here in the default behavior of testing, when there's no test adulation, so the generic script is like this. So all the tests will be running in one JVM process. And in case we want to use test adulation, but with sequentially running all the tests, the generic script is like this to run each test in its own JVM process and one after another. And in this example, when we want to use parallel testing, the generic script actually make use of operating systems process parallelization support to parallel the tests, which still runs in their own JVM processes. So FolksGrip provides a bare bones stripped down mechanism for test adulation that removes all IPC overhead. But the problem is that may not support all the configuration options out there in, for example, in Maven. As another approach to actually fix this overhead in Maven, with the help of FolksGrip, we also carefully profile Maven to identify the source of this additional overhead. And to do that, we break down the testing time into 3 parts. So T1 is the time between the build system begins running a test until the child process starts. And T2 is the time for the child process actually running the test, basically between it starts until it terminates. And T3 is the time between the child process terminates until the build system actually knows or determines that the test has completed. So we measure this 3 times for 3 build systems on Gradle and Maven. And surprisingly, we found that most of the overhead in Maven actually come from this T3, which is after the child process has finished test until the build system actually knows that the test has completed. So with a closer look into that, we actually found that's because of a performance bug, where the child process keeps reading from standard input, and due to a implementation detail in JVM, the build system wouldn't know that the child process terminated immediately. It will have around 300 millisecond lag, which explains the T3 overhead here. So to fix that performance bug, we actually went over many iterations with Maven developers for several months. So initially, what we prepared is a large patch that where we try to remove all the sources of this overhead. And but the patch was too large with many massive changes to many files, and it was hard for Maven developers to review and interpret those changes. And then we actually went on another road to prepare a smaller patch with just change several lines of code. It was easy to inspect, but didn't remove all the sources of overhead. And that was actually already accepted and merged to Maven show file in the latest version. And that patch is still very effective. So we did this measurement again with Maven with our patch. So basically that removes the T3 overhead effectively. And to additionally evaluate the effectiveness of FolksGrip and patched Maven, we did perform an extensive evaluation where we asked these 3 questions. So first was performance improvements obtained by FolksGrip compared to the unpatched Maven. Second, how does that improvement scale as the number of concurrent processes increase? And third, how does the patched Maven compare to FolksGrip? To do that, we selected 29 open source projects as subjects from some recent testing literature, and they need to use Maven build system, and we require that they have non-trivial number of tests, and the execution time is non-negligible, and they need to be successfully built at their latest revisions. And in total, we have 2 million lines of code in our corpus, and around 6,000 test classes and 200,000 test methods. And for each of the projects, what we do is we will clone the project from GitHub, and then we execute the mvn install to download all the necessary dependencies from the internet, and then switch to offline mode to avoid being affected by those downloading times. And then we will run the test using FolksGrip, unpatched Maven, and patched Maven respectively, and measure the test execution time. So our first question was to compare FolksGrip with unpatched Maven, and basically what we do is we run the Maven testing command with Tessellation sequentially running the test. And this table shows the summary line of all the results for all the projects, and those results can be found in our paper. So TMVN here is a test execution time for the unpatched Maven, and TFS is testing time for FolksGrip. And RT means reduction time of FolksGrip compared to the unpatched Maven. So we found that FolksGrip reduces testing time by 50% on average, and it could be up to 75% in some of the projects. And another observation we made is projects with smaller tests, which means each test will run less time, they benefit more from FolksGrip. And in the second question, we want to see how does the improvement scale as the number of concurrent processes increase. So we run this Maven test with Tessellation again, but in this case, we use for count equals 2, which means 2 processes will be running in parallel. And we found that the savings obtained by FolksGrip is now 32% on average and up to 63% for some projects. And this reduction in savings compared to sequential runs is also expected. because the total execution time is approaching the theoretical maximum when the number of concurrent processes increase to, for example, infinite. And basically, that's the time to execute the longest test. And in that case, the overhead of IPC will be negligible. And the third question, we want to check the effectiveness of the Maven without patch. Basically, here we run test evaluation in both sequential mode and parallel mode, where fork1 is the sequential mode and fork2 is the parallel mode, where two processes can be running in parallel. And the T new here is the test execution time for the patched Maven. So as you can see here, the patched Maven substantially outperforms the non-patched version. And we found that the FolksGrip still slightly outperforms the patched Maven, which is also expected because, as I mentioned, like our patch didn't remove all the overhead, all the sources of overhead yet, and there's still ongoing work to remove all of those overhead, which we are also engaged in. So before I end my talk, I would like to share some implications and lessons learned from our experience. So I won't have the time to go into all the details here, but they are in our paper and you are welcome to check them. So the first implication is we found that detecting performance bugs, so differential testing is very useful. So performance bugs are hard to find, but when there are alternative systems that can accomplish the same goal, which in our case is we have 3 build systems that all implements Tessellation. We can use differential testing in this case to help review performance bugs there. The second implication is to find simple fixes that can be integrated today. So basically, our smaller patch is already helping developers to save significant time of testing, while that long-term fix, the larger patch, is still like going on to so although that long-term fix may be more appropriate, which it completely removes all the overhead sources of overhead, we find that it's just to having a smaller patch and easy to inspect patch to be integrated soon, it can also bring more impact to the community. And the last 2 implications are for researchers. Basically, we suggest researchers should engage more in the open source community, for example, in the forms of bug fixes, pull requests, and actually some new technologies like Slack channels, which we did for fixing this performance bug in Maven. And the case to find a balance between research novelty and practical impact to the community. And lastly, we suggest researchers can continue to have more work on testing the build systems. So to conclude, we demystified why test adulation is costly, and we actually found a performance bug in Maven related to inter-process communication. We developed FolksGrip, which is a research prototype that minimizes the inter-process communication overhead to speed up test adulation. And we performed an extensive evaluation to confirm the effectiveness of FolksGrip. And finally, our patch was already accepted and merged to Maven, which is already saving significant test execution time for many developers. So with that, I would like to wrap up my talk. And thank you for listening.
Thank you very much, Pengyu, for this nice talk. And we have a couple of minutes for questions. There is a question on Slack from Shovik Mondo. I will also post this question on Zoom so that you can see, and as it contains some information. So regarding parallel test execution, were the test loads evenly distributed? I mean, whether balanced or imbalanced loads were observed? How does the performance scale with increasing number of parallel processes? I mean, for a system with 40 virtual CPUs, will the performance always increase with increasing parallelism from 2, 4, 8, 16, 32? Or somewhere around 18 threads, there will be a peak and a dip will be observed in terms of speed up thereafter? And also mention about gray work.
Thank you. Thanks for the question. And Yeah, basically, we did explore some of the different parallel task execution distribution ways. So the script I showed in my presentation is actually the simplified one to help you just understand the idea. But basically, what we found is that actually this introducing another some complicated mechanism for distributing the workload across processes that could also bring some overhead. So in most of the times, the simplest way to basically evenly distribute basically based on the number of tasks to each process is usually the most efficient one. And we did experimented with more CPUs, and so actually we found that the performance basically the in terms of the time for running tests, it will drop when the number of processes increase, and the overhead of the IPC overhead and thus the benefit bring by FolksGrip will also will go down a bit as I explained in the slides. And so we experiment up to actually 16 processes in our preliminary study. So we are not yet to see that peak mentioned in the question yet, but yeah, that's a good question, and I think more work can be done there.
So thank you very much, Pengyu, for answering this question. And if there is any further follow-up, I welcome everyone to use Slack. So we had a great session, and I invite you to stay connected, and that in 20 minutes we will have a